Welcome to Ask and Learn.
We want to produce graphs of f of x equal to 6 times sine x minus x squared on the interval -5 to 3. That reveals all the important aspects of the curve, and in particular, we want to look at the graphs of f prime and f double prime to estimate the intervals where the function is increasing and decreasing, any extreme values, intervals of concavity, and points of inflection. So you might notice I have these three graphs here. So the first graph is just what I got when I plugged this into my calculator on the interval -5 to 3. So it looks like it captures the essence of everything. But maybe if we use calculus, we might find that some of the points or some of the behavior is kind of hidden with just how the shape of the graph is. All right. So let's go ahead and first start by finding our points of increase and decrease, or our intervals of increase and decrease. So remember, that is going to be where f prime of x is strictly larger than 0. This tells us where the function is increasing. Now maybe I should give a little bit of intuition as to why I have them cropped like this. So all I did was make sure that for the derivative and the second derivative that I captured all the intercepts that the graph had, because anything we care about for these function will be just revolving around our critical values and our inflection points, which are all going to be x-axis. So I really don't care about the overall structure of it to find where it's increasing, decreasing, and anything else of importance. So we can go ahead and use this now to find. So it looks like to the left of -2.938, the function is positive, so it would be increasing there. And we know we need to stop at -5 since we're not going to infinity in this case. So our first interval of increase will be -5 to -2.938. Then after that, it starts increasing again at -2.663, and it keeps on going all the way until 1.17. All right, so that's going to be increasing. And then decreasing is when f prime is strictly less than 0. And this would just be the remaining interval of our domain. So the function is going to be negative from -2.938 up until 2.663. And then we're going to union that with, well, it becomes negative again after 1.17, and this is going to stay negative all the way until our other boundary or endpoint being 3. Now, what we can go ahead and do is check to see if these are maxes or mins. So starting all the way on the left, to the left of that, f prime is positive, so it's increasing into this point, and then it's going to be decreasing afterwards. That tells us we're going to have a local max here. Then, for our other one, we're decreasing into it and then increasing after. So this is going to be a local, not local max, local min. And here on the other side, well, we're still increasing into the point and then decreasing after. So this here will be a local max. All right, now we can go ahead and look for concavity of our function. So remember, this is going to be concave up when f double prime is strictly larger than 0. And we can see that that occurs between -2.802 up until -0.38. And then the rest of this will be when f double prime is negative or strictly less than 0. which would tell us where it's concave down. So it's going to be from -5 to -2.802 unioned with -0.3823. And here we start concave down to the left, and then after this first point will be concave up, so this will be a point of inflection, and our other value, it starts concave up and then goes to concave down, so this other point will also be a point of inflection. All right, now I went ahead and took those 5 values that we got from the last part. So these first 3 are all of our local max mins, and these other ones are inflection points. And I use these to figure out what my scale for y should be. So the x was already determined. It should have been -5 to 3, so I didn't really need to play around with that. And I saw that my largest value was here at about 4.1, so I just needed to make sure I was a little bit higher than that at 5. And I chose my bottom window to be -20, even though the smallest value that I end up getting produced is about -9.9, because I also wanted to check for my endpoints to make sure that neither of those ended up being a maximum or min. And it just happens to be that at -5 we end up with a global min. So I just went ahead and went out a little bit more for the interval. Now this looks pretty much, I mean, it is exactly the same graph that we had before, but if you look at all these little dots, these are those 5 points I have over here on the left in my chart. And we have this cluster of 3 right here. And if you were to just look at that, you might overlook that in the original graph and just say, oh yeah, that would just be a point of inflection, and you would never possibly guess that there might be a local min and a local max there. And if we blow this up, which is this graph over here, we can see that indeed this here is a min, this one here is a max, and that middle point is a point of inflection. But like I was saying, if we just looked at that first graph and we didn't use a little bit of calculus, we would have never saw that if we blew up that little rectangle right there, we had some extra pieces of information that we were actually missing.